Hello everybody, welcome back. Today we're going to take a look at tensors, which are kind of weird and hard to visualize, but hopefully we can figure that out here by the end of this video. Okay, so here's our question, or our problem. Write the triple scalar product in tensor form and show that it is equal to the determinant. So basically what we have here is we want to prove this here um, in tensor form instead of in vector form. Um, so the first thing we're going to do, and you'll see why a little bit later, is we're going to get rid of all the x's and y's and z's. Instead, we're going to think of it as 1, 2, and 3. 1, 2, and 3. 1, 2, and 3. Um, and then I'll just write what this is equal to so that we can double check at the end. If we get that this side of the equation equals this over here, then we also show that it equals this, and thus we prove it. So we all know how to do determinants of matrices. Um, we also know how to do uh, triple scalar products. This is all stuff that we've been taught before, but doing it in tensor form is going to be a little different. Okay, and this is a C2. Yeah, you guys can see that well enough. And then minus A3, B2, C1, minus A2, B1, C3, minus A1, B3, C2. You can do the basket weaving approach, or you can do it the proper way. So tensors. So before when we were doing matrices, um, we would add dimensions by adding rows and columns to our matrix. So we would have like a two-dimensional vector, which would be just a, you know, a b, and then we would have a three-dimensional vector, which is a b c. Um, Tensors do that slightly differently. If you want to think of it as dimensions, they're officially technically called ranks. So a zero rank tensor is just a number. Um, second or first order, a first rank tensor is a list of 3. A third is um, yeah, actually it would be more correct to say A1, A2, A3. Um, a second order tensor would be A1, 1, A1, 2, etc., etc., etc. There's 9 of them in all the way up to A3, 3. And then once we go from, a point to a line to a plane, technically, if you think of it of that way of numbers, the next way to go is actually to have a cube of numbers. And that's kind of what's illustrated here. This here is a special uh, third order tensor. Excuse me. I don't know why that's not erasing. Oh well. So that's what we'll be dealing with. Uh, it's a cube of numbers, so there's 27 numbers in all. But we'll get to that in due time here. First of all, we have to put this into tensor form. Um, and these tensor facts down here will help us. We'll start by doing this B and C here. So A vector, B vector, C vector. Putting it into tensor notation, um, for B and C we get that it equals this special tensor ijk, um, bj ck. So and then this would be dotted with our a. So if we replaced this here with d, then we get that this is the direct product. And since this is already indexed to I, and this is also, then we don't have to deal anymore with that. And in fact, we're just multiplying it directly by AI. So this is this in tensor form. I'll make it a little more clear that that k is a subscript. So how exactly do we do this then? Another thing that's important to remember is that in these equations they're using summation notation. So that means that if there's a equation that appears, or a index that appears twice, exactly twice on on the same side of an equation, then you're actually summing over that variable. So for example, we're summing, since there's two j's and two k's, we're summing our j's and our k's on this side. So this is j from 1 to 3, k from 1 to 3, and that's e, I, j, k plus bj plus ck. So it's kind of confusing at first as to why um, these summations are left out. But ultimately, it's just to save space, and you can, once you spend some time working with them, you can see how you can see that without having to write it in every time. But we'll write it in this time. Um, so, uh, so yeah, the dot product, as you can see, it's just you take your two vectors and you sum. You have the two indices and you just sum over. So it would be like so this would be the same as saying a1 d1 plus a2 d2 plus a3 d3. It's just a lot more condensed to write it as ai di and have the rest of it be implied. So with this being the case, now we can rewrite this. We're actually summing over the. Actually, I'll tell you in just a little bit. Once I finish writing this out. AI B J C K. So we're actually summing over this entire cube here. From I is 1 to 3, and then j is 1 to 3, and then k is 1 to 3. So this actually we're summing over this entire cube of numbers here, and so we can obviously, as you can see, this special tensor here, most of the values are actually 0. So it's more instructive to actually look at what values aren't 0. Also, there are tons of interesting properties about this this tensor here. If you look, if you can kind of visualize it, any slice you take of it in any direction is actually it's going to have a 1 and a negative 1 in it. Um, and there's other cool things, the diagonals and all that you can uh, look at later. But so let's first see where this special tensor is equal to 1, and then we'll list them all, and then we'll look at where it's equal to negative 1. So our first one that we see here is, look at our coordinate system here. It is 2, 3, 1. And since we're summing over this, when we have a, whatever number we have in here, it's the same number here as it is there. So this is going to be, our first one is going to be, it's going to be 2, 3, 1. So that's going to be A, 2, B, 3, and then C, 1. Because, yeah, the point that it's located at gives us the indices. So then also, our next one is at 1, no, it's at 3, sorry, it's at 3, 1, 2. 3, 1, 2. Okay, so that is going to be a 3, B, 1, C, 2. And then our last one here is, it's going to be 1, 2, 3. Yeah, 1, 2, 3 actually. So that's going to be A1, B2, C3. And then where our negative ones are, our first negative one is at, it's at 3, 2, 1. 3, 2, 1. 3, 2, 1. And then our next negative one is at 1, 3, 2. It's going to be 1, 3, 2. And then our last one is going to be equal to it's going to be 1 no, it's going to be 2, 1, 3. 2, 1, 3. Okay. So this is the result of our of all the operations that we did on our tensors. So if we look here, these are equivalent. I wrote them in a slightly different order, but this does equal the determinant that we saw before of A1, A2, A3, etc. B1, B2, B3, C1, C2, C3. Yeah, well, I can't really draw that. It's too close to the side of the screen. There, that works. Okay, so we've shown that, that this is the case. So even when we even when we use tensors instead of vectors, then the math still works out with what we know about tensors, and we still get the same results as we would if we used our normal familiar vectors instead. Thank you so much for watching, and I hope to see you soon.